Okay, I guess we're gonna get started. The topic for today is multi-echo EPI, not to be confused with multi-band or simultaneous multi-slice acquisitions. Hopefully, at least that won't be one take-home message that you can take from here, the difference between these two. The talk is divided into a series of sections. I will start by, I guess, introducing what multi-echo fMRI is. Then we'll talk a little bit about once you have this other way of acquiring your data. So the main difference here is we're gonna get more data than we normally do. Instead of having a single time series, and I'm getting a little bit ahead of myself, we're gonna end up having more than one time series per voxel, and they're all kind of concurrently acquired. I'm gonna go through several of the different things that you can do with this extra rich data set in order to actually hopefully do some better job at the noise in your time series and therefore to get better results in your statistical analysis. Then I will focus in one particular way of doing things, which is MICA, which is a method that was developed in our labs a few years ago, and they still under developing. And I will go a little bit into the details of how it works, but I will not be able to tell you every single step that it does. And then I'll finish with some applications kind of to demonstrate that MICA might be potentially a good way to go into your own studies. So hopefully by now, we had a lot of lectures in this course, and I don't need to justify why we need to try to do our best at denoising the data. But something that maybe not all of you do, it's, so here we have on one side, I have the pointer here, yeah. On one side, we have raw data as it comes out of the scanner. Oops, sorry. And on the other side, we have the same in terms of signal percent change. So all I've done is basically take the time series, compute the mean across time in every single voxel and divide it by it. If I play a video of those time series, you know, they look quite good. I mean, we see some fluctuations. We might see some things happening here around the eyes. If we're big believers, you might say you can see some of the pulsatility around here, but overall it looks pretty clean. This is the same data set. But once you look at it in terms of signal per units, you can see there is a lot of fluctuations. And in a second or so, you will see something related to motion, and you suddenly see that there is this artifact all over the place. Now, it's important to look at your time series like this, because this is really what then you're doing your analysis on the small fluctuations that happen on top of the average signal and on what happened across time. That's where the value in fMRI is. So, oops. Okay. So on your regular fMRI, what you have is you have an experiment that's going to progress across time. You set your TR to whatever you think is the best option. Usually it's a balance between temporal and spatial resolution, how many slices, how small or big the boxes are going to be. And then within a given TR, you acquire a series of volumes, all the slices. And what that happens is you have your excitation pulse and a single readout window. At the end, what you end up is with a time series of volumes that if you were to go voxel by voxel, you end up with that single time series. This is the case of a block design, it looks like, so we can see very clearly these activations going up and down. We can also see they contain some noise. What's the difference in multi-echo fMRI? Well, in multi-echo fMRI, what we're gonna do is when we have that excitation pulse, instead of just doing a single readout, at an echo time relative to that excitation pulse, we're gonna do several of those. So we're gonna do in this particular case 3 of them. What that means is that now, instead of having a single time series per voxel, we have 3 of them. 3 of them, and the only difference, hopefully, is that they've been acquired at different echo times. Because echo time affects the amount of ball weighting, ball being what we're really interested in our signal, these 3 time series are gonna have different values of that. That is different to multiband. In multiband, what happens is that at every single, what you do is you excite more than one slice at a time. Therefore, you can get more, you can reduce your TR. Here, we don't. Here, what you get is more time series, but this is not gonna help you with your temporal resolution. If anything, it will do the other way around, but just slightly. So why this is a good way of doing things? Well, there is no SAR cost because what you do is to read out more times, usually in times that are kind of idle, so you're not having more problems in that sense. You may have a slightly loss in temporal resolution because, to acquire maybe the last echo, you decide that you needed a little bit of extra time. By the way, nobody says 3 echoes is the magic number. We tend to do 3 echoes, but maybe it's better to do 4, and that's open for discussion, or 5. And you might have a slightly loss in spatial resolution just because as your echo times get longer, your signal has decayed more. So you have to have some signal. That's why we don't acquire, 20 echoes or even 7 echoes, because there won't be no signal left. But in order to have some signal, even at the 3rd or 4th echo, you want to make sure that your boxes are not too small, because the size of the voxel affects the level of signal. But overall, the take-home message is that if we were able to get this type of data, you really are taking a very small hit, potentially in spatial or temporal resolution, and suddenly you have a much richer data set. So how does it look? So here is an example of 3 volumes acquired at 3 different echo times. And the first thing to see is that, well, first of all, of course, there is different, where is this, the mouse? There is different intensity levels, but the first thing that usually, and that's one of the reasons why some people like to do multi-echo, is that at shorter echo times, we start to recover signal in these areas that usually in our regular echo time, which usually is the one that we use at the middle echo, you almost have no signal. So you have recovered signal in areas that are affected by dropout. That's one gain, potentially. For the first few slides that come now, there's going to be some formulas here. Just don't get too scared. I'm not going to try to derive them, but I hope that they help to navigate through the type of things that we can do with the data, okay? So here we have a slice in the brain, and here for 9 voxels in this little square, we have the time series. So what we measure is the signal. If we focus here, we have the signal in a given voxel across time, and these particular traces in black are all at one of the echo times of the 3 that we have in this data set. One potential model for that signal, as I said, a given voxel at a given moment in time and on a given echo, is this one, in which we have fluctuations that are independent of echo time and fluctuations here that are multiplied by echo time. And it is these ones that are ball-like fluctuations, the ones that are going to be related to a given extent on neuronal activity or something of interest. And then, of course, we have noise. So I think I just went a little bit ahead of myself. Here we have one term that captures local fluctuations due to T1 changes, for example, inflow, hardware instabilities. And we have a second term that captures the local fluctuations in field inhomogeneity, including ball, which is our target. Those fluctuations, both for the S0 and for the R2 star, we can think of them as a mean value and a small fluctuation sitting on top of it. That applies both to the S0 and to the R2 star. And when we do that, the assumption here is that this small fluctuation is much smaller than the mean. That's what we say here and here. And also, because the mean goes here, this fluctuation has a mean of 0, okay? So this is clear so far? Okay. And those are different things that now, as we move forward, we'll be able, you will see that when we have multi-echo data, we might be able to actually get estimates of these things separately. Okay, so that takes us into what can we do once we have acquired multi-echo data. Here are just these little formulas here to keep them in mind. So by definition, as I just said, the average across time of the fluctuations in S0 and R2 star at 0, because I calculated the mean and put it on a different term. And therefore, it follows that if I take this guy and calculate the mean, which would be the mean in a given voxel of my time series across time, this is what I end up with. So the mean time series across all time in a given voxel and a given echo time, I have information about the mean S0 and about the mean R2 star. And just by doing a little bit of math, getting the logarithm and moving things around, we can end up with a linear system, and the take-home message here is that this can be easily solved, and I can get maps of S0 and of R2 star, their mean values, not their fluctuation, just their mean values. If we were to do that, we can get maps like this. So here we have a static map of S0 and a static map of T2 star. This maps is to a given extent quantitative, although you have to think that, we just have 3 data points, and we're doing some math that whatever noise that is in the data is going to propagate. So Those are not perfect maps, but still, it's one extra bit of information that we have. We can see that this one captures very well the intensity and homogeneity due to the coils. And here we can have a map in which, we can see how the T2 star varies in the ways that we would imagine given the different tissues here. So that's one thing we can do. Not that interesting from the point of view on fMRI, but still, it's some extra information that we have. What we're really interested in fMRI, it's in the fluctuations, in the other term. So if we put again the same formula that we have here, where is the mouse? Here. But we substitute this by these two guys and substitute this guy by these two guys. We have this. It's a little bit bigger, but it's just that. The next step is to actually take this definition that we have here that contains the mean values and put it apart. So we have extracted it and we have this new formulation. It's just algebra, moving things around. There is not that much. The first approximation that comes is this one. In order to make the exponential something linear, using Taylor expansion, we can substitute it by this. And the whole idea is once you do the math here, this term, because it contains the multiplication of two things that are very, very small, we can just discard it, and we can simplify the formula, and we come to something in which we have things in terms of signal percent change, because we have the signal that we measure in every voxel at a given moment in time across echoes, minus the mean divided by its means. It's approximately equal to the summation of two different terms. One that we call delta rho, and that one contains the fluctuations of no interest in terms of signal change, the fluctuation divided by the mean, and a second separate term that contains the fluctuations of interest, okay? You can walk later through the math if you want, but the whole idea is, again, by very simple math, we can pull these things apart just by doing a couple of simplifications. So we can do that in our data. So again, here we have a series of voxels. This is what comes out of the scanner for a given echo, echo 2. If we do math similar to the one that I just showed you, we can subdivide this in two time series. One of them would be the fluctuations of interest in green, and the other ones, the ones of no interest. And in this case, in which things work quite well, but again, I wouldn't recommend this because all this approximation, whatever noise is in there, will propagate. We can see how by doing this, the slow drift was most of the time very well separated in these components of no interest. And then what it's called the RT2 star ended up having this kind of flat appearance, which makes sense because we know that our signals are contaminated by slow fluctuations that are related to the hardware, not really to Ball effect in this case. And I will get later on how this is one thing that when you do SMICA, it works pretty well and can be used for pharmacological studies. Another way of looking at this is, again, if we use Instacore, which is this tool in AFNI that allows you to compute the correlation of the signal in a given voxel to everywhere else in the brain on the raw data, we get a map like this that we could argue there is some contamination here. If we do it on the delta S naught time series, it seems that we're capturing all the artifacts. But if we do it on the other ones, suddenly we seem to have a much cleaner map. So this gives you an example of how these things can help a lot to clean up the data. That's one way of doing things. As I say, it's not the optimal way, and I wouldn't do it with 3 echoes. Okay, I'm using here a kind of a good example. Other thing we can do is simply to think, okay, suddenly I have 3 time series instead of 1. The theory tells me that when I have 3 noisy measurements of something, if I combine them, I tend to get a better estimate of what the actual value of that I'm measuring is. And people have done this. You can think about just simply doing the summation of the echoes or doing perhaps a little bit more smart way of doing this, which is a weighted average that is supposed to optimize for contrast. But I mean, the whole idea is that you have these 3 time series and you can go and combine them. This may be better than the other one in the sense that, the math is much more simple, but also you have to think that whatever artifact is present in all of them, and the things like motion are going to be present in all of them, here they're going to be still present on the average, okay? So it helps you with signal to noise in the sense that any random noise across them will go out, but maybe there are better ways to do this. Here is the example of single echo versus optimally combined, and if we were to look at the TSNR, the next thing we will see in that in these regions of dropout, just by doing this simple combination, we actually gain in TSNR. So it's a good idea. It's just that maybe it's not the best way of using this data or getting the most out of it. But definitely optimally combination is one way of doing things, and you might get better results. The next more advanced way is what is the basics for MICA. And the idea here is to do an echo dependence analysis. So are things clear so far? Okay. So again, here is our formula about what the signal level in a given voxel at a given moment and for a given echo time looks like. And what I'm gonna show you here is how that signal level changes as a function of echo time for one particular case. Okay, let's assume that for this voxel and at this moment in time, S0 is 5,000 and T2 star is 30 milliseconds, which are regular values. And what we would expect is the normal decay of the signal as echo time progresses. That's why when I was showing you the images for different echo times, they look less and less bright. If from one moment to the next there is some activation, which means a change in T2 star, we get a slightly different decay curve, okay? So the only thing that has changed from this one to this one is that the T2 star has changed, which is what happens when an area gets modulated by a task. If we do the subtraction of these two curves that you see here, we get a curve like this, and this is normally the curve that gets used, that is used to actually decide what's the optimal echo time that you use. When you go down to the scanner and you do your single echo fMRI, you usually one of the many parameters, you set up your flip angle, you set up your voxel size, TR. Another one, it's the echo time, and that is usually chosen looking at curves like this, and the theory tells you that in general, your optimal, the echo time that you should select should be equal to the T2 star of the tissue of interest, and that's because that's how you see it at the top of this curve. If we look at this curve in terms of signal percent change, the beauty of it is that suddenly we have a linear relationship. So what this tells me is that if I have a signal fluctuation that is due to a change in T2 star, which is what we're looking for, then I should expect that if I look at my signals in terms of signal percent change, I should expect a linear relationship with echo time. That's the take-home message here. So we put that on one end, and now what happened with the other one? What if I have two curves that the difference between one and the other is not a change in T2 star, but a change in S0? So this would be hardware instability, this would be head motion. Then what happened is the curves look slightly similar to this, but not exactly. And when we do the difference, they look less similar to that. But more importantly, when we look at them in terms of signal percent change, there is a clear difference. That's the key to the whole echo-dependent analysis. The signal fluctuations that are related to changes in T2 star will show a linear dependence with echo time, while signal fluctuations that are due to changes in S0, and therefore usually artifacts, they will have a flat relationship with echo time. And this is what we're going to explore for the rest of the analysis. So how does this work? So here we have a multi-echo data sets, which has been saying, it means that for each single voxel, we have 3 or 4 time series, 3 on the, in this case. Here we have what we just have learned about the different behavior of signal fluctuations in relationship to echo time. And then here we have, as we normally do in an analysis, our expected response. For example, if this was a block design and there was 20 seconds on, 40 seconds on, this would be what we would be looking for during our GLM. So what we can do is say, okay, so let's look at this. I think that this signal is present in my data. So the first thing I'm gonna do is I'm gonna take this signal and I'm gonna try to see how well it fits in every single voxel. So I will get this, think of this of map of beta estimate across the different echoes. The next thing I can do is, okay, if this is truly ball-like, I mean, it's the result of neuronal activation, when I look at the different fits, these fits in this voxel should follow this type of model, not this type of model. So I can actually calculate the goodness of the fit to either this model, after I have done the fit of the time series to every single voxel time series, or the fit to the other model, okay? So this is basically how well the effect size of this time series varies across echoes following this model or that model. And of course, in different locations of the brain, it's gonna look different. But overall, hopefully, there will be a potential behavior going in one direction or another. So the next step is to take these maps and compress them into a single metric, and that's what's normally called the kappa and the rho within the nomenclature of MICA. So kappa tells you how well your signal across the brain or across a subset of the brain, if we're looking to components, fits this model, where the rho tells you how well that signal across the brain fits the flat model. And things that look like having a kappa much higher than the rho most likely are things that I should care about because they come from the Ball effect, and things that have a much higher rho than a kappa most likely are artifacts, okay? Of course, and I will get back to that in a second, if we're doing rest, I don't have this, how to call it, not representative, but these signals that I want to go looking for. I don't know what to look for. And that's where the ICA step comes handy. We'll do an ICA on our data to come with a series of signals that we know are present in the data, and then we'll use the echo dependence analysis to discern whether those signals are most likely to be of a ball origin or not. Is that clear? Any questions? Okay. Yeah. So the question was, and from now on, please, whenever you have a question, use the microphone. I've been asked. The question is how strong the assumption of linearity is. Those models are true as models. The problem is that in your data, whatever signal that you're going to be testing, most likely it's still a combination of things. And I mean, for example, now in a second I'm going to explain MICA. So we're going to do an ICA decomposition. We're going to come with a series of signals for which then we're going to test whether they fall one of these models or the other. Well, no signal is going to fit any of these models perfectly. The hope is that it would fit one much better than the other. But as I will show, sometimes the algorithm may also break. This is just one way in which you can automate a lot of things, and it tends to work quite well in many instances, but it's not perfect. Because on real data, that answers the question? Okay. Any other? So, MICA. Disclaimer first. I'm going to go over some of the details of it, but MICA has been evolving in the last few years. Porantic has been taking care of it, and most likely what I'm going to explain here is not the latest version of MICA, okay? So if you're going to be using the latest version, which I think is 3.2, some of the things might actually differ. The generic concepts are correct, but if you see some inconsistencies, just be aware that things have evolved. And we here are trying to develop other alternatives of doing things. So I'm going to try to go over the generic concepts that apply to everything, but there might be some discrepancies. So as I was saying, we getting our data as multi-echo data, not a problem. Having our model, not a problem. But if we want to do this in rest, the next thing we know is to have these time series that we want to use as reference to decide whether they're noise or not. And one way of doing this is, of course, you want to extract time. You want to use time series that are present in the data. And one way of doing this is ICA. ICA is widely used in fMRI, both to find networks of interest, but also is well known to capture artifacts in the data. So it seems a good first step to come with these time series that we're going to then check whether they're good or bad in order to remove them. So here is an example of what happens. So this is, I thought I had a graph here. No. So this is for one time series that comes out of the ICA. The first thing you do is you do the fit of that time series against each of the echoes on every voxel, and it gives you maps like this. Then what it will do is to compute the goodness of the fit for one of the models or the other model, and compute that average kappa and rho, which is somehow a summary metric of these maps, although how it gets summarized, it's a lot of detail in there. But for this particular case, in which we can see that definitely it looks like a good component, it's very clear that this would end up with a kappa that is much higher than a rho, and that's a good start for the algorithm, okay? If we were dealing with something, not only that, but also the time series associated with this component, which is here, looks like something plausible. Here is an example of a component where we see something that definitely doesn't look very much like bot-like, looks a lot like an artifact. If you were to do the fit of this against the data, you would see that it appears as a ring, and it appears kind of flat in all of the echoes. So when you actually do the fits of either one model or the other, it seems to fit this model much better. And when you calculate these summary metrics of kappa and rho, this is an example in which the rho it's greater than the kappa. You do these things experimentally, and what happened when you do an ICA, I don't know how many of you have done ICA on fMRI data, but when you look at your ICA components sorted just by the ICA ranking, it's not like the good components are always at the top. You kind of get a mixture of things. But when you actually sort your components in terms of the kappa and the rho, the story is much different because they're based on those properties that are supposed to segregate these things. If we were to actually sort the ICA components based on the kappa, empirically, it's been shown that it has this type of curve in which there is a clear slow decrease and then there is an elbow. And it seems that most of the components that are below the elbow are very good, are ball-like components, our typical default mode network, and many of the other resting state networks that we're used to see, while the components on the other side of the spectrum, and here is some for the, this is wrong, so sorry. It's this part here. They're also sorted by kappa. So these guys here tend to be the components that look like noise or artifacts, okay? And that's what the algorithm is gonna explode as information to do an automatic. I mean, the idea here is you can have single echo data, you can do an ICA, and then have people that goes through each of the components and decide whether it's noise or not. The idea here is that by having multi-echo, you can do that in an automatic manner. Nothing precludes you from having single echo, doing an ICA, and with your knowledge, deciding what's noise or not. Here, you can automate that. So how does the algorithm works on the inside? Just for those of you who might be interested in using it. So the MICA package, as it is provided, or the set of scripts that form MICA, will do beginning to end. They can take the data out of the scanner, do all your pre-processing, and give you the denoise time series. That doesn't mean that that's the only way of using it, okay? If you want, you could do your own pre-processing and then jump halfway through, and then based on your favorite pre-processing, then apply the echo-dependence analysis only, okay? As part of the pre-processing, it contains the typical slice time correction, head motion, and registration to anatomical. But as I said, don't feel that that's the only way that you can do things. The next thing that it does the optimal combination that I was talking. It takes the 3 echoes and that a weighted combination and uses that as an input to a PCA first to estimate the dimensionality of the data, basically how many components. This is normally do when you do a normal ICA. There is always a PCA first to estimate the dimensionality and to get rid of random noise, and then there is the actual ICA. So this works the same way, with the only difference that both the PCA step and the ICA step, the selection of the components is not based on the amount of variance explained, but based on the kappa and the rho. And then at the end of the whole thing, it will throw you a series of files that I will mention some of the most important ones that then you can take as the input to your statistical analysis. So think of it as a different way of doing your pre-processing, or as an extra step in your pre-processing. So as I was saying, for the PCA decomposition, there is the PCA itself. For each of the components, there is the characterization, meaning it computes the kappa, the rho, and potentially other things. There is the component selection, which is not based on variance, but based on those other characteristics. And it selects a few of them, reduce the dimensionality, create some optimally combined time series again after the PCA, and those are given to the actual ICA step, and the same thing happens. The ICA, then there is the component characterization, which means for each of the components computes the kappa, the rho, and here a lot of other things. Then there is the component selection, and for the components that the algorithm decides that they're good, it puts them back together, and that's your denoise time series that then you can use in your statistical analysis. So I'll just give a few details, but if you really want to understand the algorithm completely, well, if you want to understand it completely, download the code. This is all widely available code, so you can go online. AVNI provides one version, but Prantic has a GitHub where you have the latest version, and the whole code is there. But if you don't want to go through the Python code, I would say those are some of my favorite papers to look at, and in particular, Appendix A, or the appendix of this particular paper, I think it does quite a good job at explaining the algorithm in detail. So for the PCA part, the most important things is to understand that it helps decide the number of components, and also that it's not a normal PCA in the sense that it doesn't do it saying I'm gonna keep 97% of the variance, but it does it based on those kappa and rho metrics. And that's just a very simple way of saying the rule, but the whole idea is that the things with a good kappa or with a good rho are kept, because the idea here is to keep things that are signal in this first step. Doesn't matter whether they're good or bad. You want to keep them, so then you do the ICA, and then later you'll decide whether it's good or bad. The idea of the PCA is just to get the dimensionality and get rid of the random noise. For the second part, for the ICA, it does the component characterization, and here is where there is a lot of metrics in the algorithm, and those have been evolved. So this is one case in which there are more things that I want naming here in the latest versions of the algorithm. But for the characterization, it looks at the variance plane. Again, variance explained by itself is not enough. We know that artifacts tend to explain a lot of the variance, okay? But if you have task-based data, task can also explain a lot of the variance. Just one of the many things that you're gonna use to take a decision. It looks at the kappa as a metric of ball likeliness. It looks at the rho as a metric of non-ball likeliness. It looks at the number of voxels in which the model, the flat model or the linear model fit best. As I said, every single voxel is going to have a slightly different fit, but hopefully something that is of a given type, there will be more voxels that fit that model very well, and a series of other things. And then in the original version, it used to be empirically defined decision tree. I think in version 3.1 or 3.2, there is actually some combination of machine learning algorithms, meaning first a clustering and then a classifier that actually takes into account all these metrics, but the outcome is the same. It will separate all the components from the ICA in 4 groups called accepted, ignore, mid-K, and rejected. But what's more important, both the accepted and ignore will end up in it's called the noise time series. That is what you're going to take to your next level of analysis. And the mid-K and the rejected is what the algorithm classifies as noise and gets taken out of the data. In terms of files as inputs, the inputs are very easy. You give it, your fMRI data set for all the echoes, your different time series that you get out of the scanner. You need to write down the echo times, so you need to leave the scanner console knowing what were the echo times for which you acquired the data, because be nice in the audience, but please correct me, that doesn't appear on the scan files, no? So you need to take note when you go down there with your experimental notebook, make sure you write your echo times. And then depending on what extra things you want to do, if you want to bring everything to a common stereotactic space, you can provide with the anatomical, you can define some of the pre-processing options, and then there are a couple of parameters that actually play with how strict the algorithm is on deciding where the elbow is for the kappa and the rho. If, as I said, if you just want to do the pre-processing yourself, then you would give to one component of MICA, which is called TED-ANA, your pre-process time series and the echo times. In terms of the outcomes, it's going to give you one of those static T2 star maps that I showed you at the beginning. It will give you a static SNOP map. It will give you the optimally combined time series, and you could do your statistical analysis on it instead of doing it on the denoise time series. So you can use MICA just to give you those. It will give you the denoise time series, which means the optimally combined plus taking out the components that the algorithm has marked as noise. It will give you spatial maps for all the components, so you can evaluate whether the algorithm did what it had to do or not. It will give you spatial maps in a different file only for the spatial components. I mean, that's just a subset of the other one. It will give you the time series of the PCA components, the time series of the ICA components, and then there are a couple of text files that contain information about the list of the affected components, the list of rejected components, a lot of information. Those things are very important to look at, but it can be a little bit overwhelming. So what we did in the last few years, especially Ben Gutierrez, who's been in our lab, was to develop a tool that allows you to look at all this information within a web browser framework. This is similar if you're familiar with FSL. When you do your ICA with Melodic, you can look at the results of your ICA analysis in the web. So here is a similar thing, and I'm going to play a little video here of So you can see the type of things you get. So it gives you TSNR maps for the different parts, for the original data, for the denoise. It gives you a histogram of TSNR, so you can see on average how much of an improvement there was. So those are interesting to look at just to get a feeling of how much it makes a difference. But the most important part, it will give you maps and time series. So here on the top, you have the information that comes on the text file with the number of components accepted, rejected, their actual numbers. So you have all that information that you can find on the text file. You have these scattered plots of kappa versus rho, and each component is marked whether it went into the accepted, rejected, middle, or ignored. The size of the symbols tells you how much of the variance was explained. So it gives you this visualization that may help you better evaluate the outcome of the algorithm. And then here you have the list of all the components separated against by group, and for each of them you get a map of the component, the time series, and the spectrum. So this I really recommend that. I know it's hard if you have like a lot of subjects and you want to automate things, but despite things being meant to be automated, a little bit of manual intervention and QA is highly recommended. And we hope that this tool can help to do that in a more efficient way. And that tool doesn't, as far as I understand, is not distributed with AFNI, but it can be downloaded from here, from this website. And this one definitely, if there are any improvements or any requests for things that you would like to check, please let us know, because this one we're actively developing ourselves. Okay. So any questions before I move into a couple of examples to show you how Mica can make maybe your life easier someday? Okay. So I'm just going to navigate through some of the papers that are out there so you have a feeling of where people have applied, and therefore, hopefully can help you to decide whether this might be a good option for you guys. So this is an example on animal data at a very high field and with extremely high spatial resolution, and we can see here what are the results of some component ICA decomposition just using a single echo, and the result after doing multi-echo ICA mean in Mica. And as you can see, you get much cleaner maps for the components. So it seems that in this type of environment, it can be helpful. I have no idea about what the networks are on the rats, so please don't ask me. Another application, and this one is very interesting, is fMRI time series are contaminated by these really slow fluctuations that are related mostly or to some extent to heating of the scanner, and we tend to get rid of them by means of doing some fitting on some filtering. But the truth is that maybe there are also some other really slow fluctuations of interest, and where we go blindly just trying to fit some polynomials, for example, in AFNI you decide the order of some set of Legendre polynomials, we might be removing things of interest. If you're doing pharmacological studies where the fluctuations that you're hoping to get are these really, really slow ones, then it's really hard. And here Mica can be one of the places where can be very helpful. So Jennifer Evans, when she was in our lab, she did this experiment in which she tried to evaluate how well Mica can help us when we have block designs, but not your normal block designs of 20 seconds on, 40 seconds off. Block designs where the duration of the stimuli lasts here, in this case, over 2 minutes, once in which kind of a flat, on-off, and another one which is even more subtle, in which the change of interest slightly goes from that on to that off position during the 2 minutes. So they acquire data for paradigms like this, and here what you have is the time series when you just have your normal regular data. This is after doing your detrending, in which, as I said, you just try to fit a series of polynomials, and then, well, it seems that this one you can still maybe capture it, but here you have killed all your information. So, it's really hard to do these things, and that's why we don't tend to do these things. But when you do your denoising with Mica, suddenly, very clearly in both cases, you can see, in this case, the block design, in this case, this is slow. And that's because the algorithm was very good at actually capturing these slow drifts that are due to artifact and separate them from the slow drifts that are actually ball-like. In terms of activation maps, of course, things get better. If we can see it on the time series, it's going to get better on the activation map. So here what you have It's the optimally combined, and on the optimally combined, you don't get that gain because, as I was saying at the beginning, when you're just doing a weighted average, whatever artifact is common to all of them, you're not taking it out in a smart way. You need something more than simple averaging because it's not just thermal noise that is causing the problem here. When you do the trending, you get something, especially for this one, as we saw in the time series, and you start to get some activation in visual cortex, which was the target for this task, but nothing for this other one. And it is the noise in via mica that actually gives you the best maps. So this is another potential application with something like mica makes sense. Another application where we have tested the potential of mica is for cardiac-gated fMRI. So cardiac-gated fMRI, the idea, regular fMRI, you set your TR, and that TR is constant. Cardiac-gated fMRI is when you set your acquisition to actually match a particular moment of the cardiac cycle, so maybe at the top of the cardiac cycle. And that is one approach that you wouldn't normally do for regular experiments, but if you're interested on the brainstem or a structure with high pulsatility, this is one option. Because suddenly that structure that is moving, by locking your acquisitions with the cardiac cycle, you're always taking the picture when they're on the same location. That being said, to do that, because the heart is not beating exactly at the same rhythm all the time, your TR is no longer constant. And unfortunately, when your TR is no longer constant, what that translates, it's into a baseline level of signal that is non-constant. And that, when that is sitting on top of everything else, is really hard to detect things. So there are some algorithms to try to correct for this because, you can go through the math, and if you have the actual differences in TR across all the different acquisitions, you can come with a model of what that baseline signal is and try to remove it. But the other way to go around, if you have mica, is those signal fluctuations are of a T1 origin. They're on the S0 part of the signal, so they're not bone-like. So the theory says that mica should be very good at capturing these guys, mark them as bad, and then leaving them out of our data. And we tried that experimentally, and it works very, very well. We don't know if too well until the reviewers approve it, but we think it's good enough. And what you always see when you run mica on cardiac-gated data is that there is always a component with a really, really high raw, meaning a really, really bad component. And that component, the time series of that component fits very well with those models of what the signal baseline would look, given that the TR is non-constant, and gives you these spatial maps that are very different to many other noise components and have this very high tissue contrast. So this was very reliable across a lot of subjects. And when that translates in terms of activation, here we did a auditory task, and there's a lot of lines here because we have to try many different things. But here what you can see that it both in terms of activation extent and in terms of the average T-stat, the magnitude, mica on cardiac-gated did much better than when you're just having the single echo. Not to mention also compared to the optimally combined. Why again? Same reason, because when you're optimally combining this artifact, which is a T1 artifact, it's present in all the echoes. By optimally combining, you're not getting rid of it. We decided to test it for task-based in general because most of the studies that have used mica have been based for resting state, so we decided to give it a go with task-based. In this case, we play with 5 different tasks on a fast event-related paradigm. And what we can see is that for all of the different tasks, there is always an increase, a significant increase in activation extent from just using the middle echo to optimally combined to mica, and the same in terms of T-stat. Significant, it's not huge. I think partly because, this was very good data. These are subjects that didn't move that much, so there is less potential room for improvement. So one thing to do is, if we have worse data, maybe potentially, I don't know, like pediatric data, which kids tend to move more, maybe we would be able to see a higher increase. But here it's still significant. It's always in the right direction. So if anything, it's just going to help you with your task-based data. People have, so now if you want to get to, use the latest thing available, there is no need to do multiband on one side and multi-echo on the other one. You can just put it all together. And there are a few sequences out there that allow you to do multi-echo, multiband, and that way you get the best of both worlds. And when you do that, there is the same paper that I recommend for actually understanding the algorithm. They saw that by using mica, you can capture very well some of the physiological noise components, which appear very clear, and you can actually see very clear due because you're sampling now fast enough. And also some of the leakages, or at least some of the artifacts associated with the multiband, they're also well marked as artifactual by MICA. And here they just have some activations, example of activations. But basically that was it. So in terms of conclusions, I think hopefully I have convinced you that multi-echo fMRI allow you to capture additional information with minimal cost in terms of temporal and spatial resolution, but there will be some cost, and that's something you need to consider when you're doing your experiments. You definitely need to make sure that the sequences are available. Such additional information can be used in many different ways to increase your contrast to noise ratio in dropout regions, that by simply doing the optimal combination, or more advanced ways by using something like potentially MICA. Some other people have proposed other alternatives. There are a couple of papers out there in which they propose just acquiring 2 echoes. The first one, a really, really short echo. The second one, your regular one, with the idea that the first echo will have very little ball weighting, and by regressing out that first echo from the second echo, you will be taking out mostly things that are artifacts. It works to a given extent, like all these things. MICA is, I hope, a promising denoising methodology that combines ICA and TE dependence analysis that will not clean every single artifact on the data, okay? It's not magic, it's just an algorithm. So it works well. It does its job most of the time, but you still need to check. And even if it doesn't work, you won't get noise-free data, and it's good to have that in your mind. It's still under development, so hopefully it will get better, and there are a lot of things that we're trying. It can definitely substantially improve the SNR of your data, and therefore the quality of your results. And just to convince you that it's worth a try, here you have an example of some time series. This is the raw data on this side. This is will be the time series of the good data, and this is the time series of what was marked as the bad data. And here you can see that here, if I find my mouse, it's kind of hard to actually see the fluctuations of interest. On the middle one, it's very clear. You can see sometimes the default mode network popping out. And here, you can see these kind of things that really look like artifact, like going from right to left. So that's all I had. So definitely a lot of people to thank. And if you have any questions, please use the microphone. Thank you. Any questions? Well, if you have questions at a later moment, just send me an email. Thank you.